This is Chapter 12, the Introduction to Organic Chemistry, and this is Section 2, Alkanes. We've seen that carbon atoms can be connected together into covalently bonded chains. In fact, these chains can get very long and branch or bend into different shapes. This produces a large variety of organic molecules, and in this section we're going to learn the naming convention for these compounds. We're going to start with the simplest class, which is alkanes. You may want to spend some extra time studying this section because the names introduced here also form the basis for the naming system of more complex organic compounds later on. Like pretty much every organic compound, alkanes are formed from a continuous chain of carbon atoms. In the case of alkanes specifically, however, the carbons are held together only by single bonds between them. There are no double or triple bonds between carbon atoms in an alkane. Since there are so many different alkanes and organic compounds in general, it's useful to have a systematic method for assigning names to them. The system that we use is set by IUPAC, the International Union of Pure and Applied Chemistry, and it consists of a root which indicates the number of carbon atoms in the chain, along with a suffix ane to indicate that it's an alkane. In this example, you see octane, where the root is oct, meaning 8, and it has the ane ending, which indicates that it's an alkane, so all the carbons are single bonded together. In this chart, we can see the first 10 straight chain alkanes. Straight chain means that the carbons are all in a continuous row without any branches or breaks in between them. The first 10 names are given in this column here, and if you look at it and you drop the ane ending from each one, you can see the prefix corresponding to that number. So for methane, the prefix meth indicates that there's 1 carbon. For ethane, the prefix eth indicates 2 carbons. Propane is 3 carbons. Butane is 4 carbons. And then after that, the prefixes follow the typical Greek system where pent equals 5, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. If you take the time to remember these now, especially the first 4, which are a little bit unusual, it'll help you later on when we name more complex compounds. We saw in the last section how you can draw the expanded structural formula for an organic compound similar to how you would draw a Lewis diagram. And so you get something like this here for the CH3 at the end of a carbon chain. To write the condensed structural formula, you just take the 3 hydrogens that are attached to this carbon and you write them next to it, like this. For an internal carbon that's attached to other carbons on either side and so only has 2 hydrogens attached, you would write it as CH2. It's condensed because it doesn't show the bond between the carbon and hydrogen explicitly. Another way to draw an organic compound is using a line angle formula, also known as a skeletal structure. This is a very simplified depiction of the molecule which doesn't show labels for the atoms at all. It just shows lines indicating the bonds. This comes from the fact that we saw when you have a chain of carbons all connected together and they each have a tetrahedral geometry, you end up with this zigzag pattern when they're all stretched out. So a chain of carbon atoms is depicted as a zigzag line in this type of structure. The ends represent carbons at the end of the molecule, and every time the zigzag makes a turn, that's another carbon. It doesn't show hydrogen atoms explicitly because those can also be inferred from the pattern of the carbon bonding. So in this example, for instance, we have 1 carbon here at the beginning, another carbon here where it turns, another here, 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 and then a final carbon here at the end. That's a total of 6 carbons. We know that every carbon needs to have 4 bonds, but these carbons don't all have 4 bonds, so we need to fill in the remaining ones with hydrogen. So this carbon at the beginning has just 1 bond going to it, so we can add 3 more to hydrogens to give it the 4 bonds that it needs. This first carbon after that has 2 bonds going to it already, so we only need to add 2 more bonds with hydrogen to get it to a total of 4. Same thing for this one here, and this one here. And then at the end, we have another carbon with only 1 bond going to it, so we need to add, again, 3 bonds to that with 3 more hydrogens. So we can recreate the structure of this molecule, which is hexane, just from that zigzag line. Just remember that terminal carbons, the ones on the end, need 3 hydrogen atoms to complete their 4 bond requirement, but internal carbons, the ones in the middle, only need 2. So let's look at another example of these three different structures for a molecule of pentane. In order to draw these, of course, we have to understand what the name pentane means. So if you look at the root, pent, that means 5 carbons. So this is going to be a 5-carbon chain. The ending, ANE, means that this is an alkane. And that means that the bonds holding all of the carbons together in the chain are all single bonds. There's no double or triple bonds. That means we can start very easily by just drawing a chain of 5 carbons. Usually the easiest structure to begin with if you're first starting out is the expanded structure. That way you can keep track of all the atoms and make sure that you have the right number of bonds for everything. So we'll begin with the expanded structure of pentane, which means drawing 5 carbons linked together. There you go. Then you have to take a look at your molecule and see what's missing, what isn't right about it. We've already accounted for the 5 carbons and for the fact that it's an alkane, so there's no more information that we can get from the name. But we can look at this and understand that every carbon in an organic molecule must have 4 bonds. So none of these carbons are satisfied with that requirement yet. For this carbon on the end, for example, it only has 1 bond going to it. And so we need to add 3 more in order to give it 4 bonds. Those 3 bonds are going to go to hydrogens. These carbons in the middle only need 2 more bonds to hydrogens because they already have 2 more bonds to the neighboring carbons. And then this carbon at the end again needs 3 bonds because it only has the 1 going to it, and so it also ends up with 3 hydrogens. And so this is the expanded structure of pentane. To turn this into a condensed structural formula, we can just take each carbon and simply write the number of hydrogens that are attached to it next to it. So this first carbon has 3 hydrogens bonded to it, so we say CH3. And then we can draw the bond to the next carbon, which has only 2 hydrogens attached to it, so it's CH2. The next 2 hydrogens are just the same, CH2, CH2, and then the last one is, again, a CH3. To draw the line angle structural formula, it's even easier. We just need to draw a zigzag that represents 5 carbons. So wherever you start the zigzag is going to be your first carbon, and then every time you want to indicate another carbon, you simply make a turn. So we begin at 1 carbon, and then turn to get 2, and then 3, and then 4, and then you end at 5. Sometimes it's helpful to go back and count the carbons in your zigzag to make sure that you got the right number, because it can be very easy to miscount. So just go 1, 2, 3, 4, and that's 5. So that is a molecule of pentane according to the line angle or skeletal structure. It's also important to remember that these molecules are not actually rigid. They can twist and turn and bend into all sorts of different shapes. So we typically draw a straight chain alkane like this, where all of the carbons are in a row, or zigzag if it's a line angle formula, or something like this if it's a condensed structural formula. But because you can rotate around these bonds and twist it into different shapes, you could draw any of these representations of this example of butane, and these would be acceptable structures for the molecule. A lot of times the person choosing which structure to draw will choose it based more on aesthetics or the space available to them than any sort of realistic depiction of how the molecule actually looks. In chemistry, the different shapes that a molecule can adopt are called conformations. For alkanes, the wide variety of conformations are made possible by rotation around the single bonds holding the carbons together. So for example, in a molecule of butane like this, you have a central carbon-carbon single bond, and then each of those carbons is attached to another terminal carbon. In this case, those carbons are both oriented upwards from that central bond. They don't show the carbon-hydrogen bonds in these terminal carbons because they're not important for the overall shape of the chain that we're looking at. So if we take this molecule and we rotate it a little bit to get a different perspective, we can see a picture similar to what we see here. In this case, the central carbon-carbon bond has been elongated a little bit to provide clarity for the picture, but that's not really important. We can still see that you have the carbon-carbon bond and the 2 CH3 terminal carbon groups pointing upwards from that. The idea here, though, is that this central bond can rotate. And so this entire end of the molecule can rotate relative to the back end. And so you end up with this CH3 group rotating down into this position that you see here in this picture. So now we have the central carbon-carbon bond still in the same place, with one CH3 group still pointing up, but the other group now pointing down. It's easy for it to do this because there's no real energy barrier to this rotation. It happens all the time at room temperature. And so if we turn this picture back into the side view that we started with, we would see that now one CH3 is pointed down and one is still pointed up. And this would bring us back to a more zigzag configuration like we're used to seeing. There's another kind of alkane other than the straight chain alkanes that we've been learning about until now. These are the cycloalkanes. Cycloalkanes are cyclic, which means that the two end carbons loop back together and bond to one another to form a closed loop or cycle. In order to do this, they have to lose a hydrogen each, and so a cyclic alkane has two fewer hydrogens than the corresponding open chain or straight chain alkane. The naming convention for these is very similar to the straight chains. The only difference is that you put a cyclo in front of it. So for instance, if you have an open-ended 3-carbon chain like this, that's propane. If you form a bond between the two end carbons, like you see here, first you have to get rid of a hydrogen from each of those carbons, which changes the formula from C3H8 to C3H6, and then you end up with cyclopropane. You have to add cyclo to the beginning of the alkane name. Cyclopropane is the smallest cyclic alkane, but from there you can have pretty much any number of cyclic alkanes. The most common are the ones that you see here. Cyclopropane, which is 3 carbons, cyclobutane, which is 4 carbons, cyclopentane, which is 5 carbons, and cyclohexane, which is 6 carbons. These can also be represented very simply in the line angle formula by basically just drawing the regular geometric shape. 3 corners is a triangle for cyclopropane, 4 corners is a square for cyclobutane, 5 corners is a pentagon for cyclopentane, 6 corners is a hexagon for cyclohexane. Let's do a few examples where we try and name some structures. Here we see 2 examples of line angle or skeletal structures. We could go through the whole process of assigning the carbons and filling in the hydrogens, but that's not really necessary. The hydrogens never affect the name of an organic compound because they always just fill in at the end. So all we really need to do is identify the carbons for each of these and figure out whether it's cyclic or open chain. So in this first example, A, we have 1 carbon at the beginning, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, and 1 at the end. So that's 1, 2, 3, 4, 5, 6, 7, 8 carbons. It's 8 carbons in a row. It's not cyclic. There's no double or triple bonds or any other atoms. So this must be a simple alkane with 8 carbons, and so that makes this octane. The prefix oct indicates 8. For example B, we have a carbon at each corner of this geometric figure. Since it's a pentagon, that gives us 5 carbons, which makes this cyclopentane. Remember that if it's a closed loop, you need to add cyclo at the beginning of the name. These examples are a mix of condensed structures and line angle formulas. In the first one, A, we have 1, 2, 3, 4 carbons in a row. They're all single bonds, so obviously this is an alkane, so really we just need to know the prefix for 4 carbons. If you refer to the chart, or hopefully you have it memorized, this is called butane. For B, we saw this example already. A triangle really means 3 carbons in a closed loop, and so that makes this cyclopropane, the smallest cyclic alkane. For C, we have to count how many carbons there are in this chain. We have 1, 2, 3, 4, 5, 6, 7, 8, and so this is another representation of octane, like we saw in the last slide. This is the condensed structure, whereas the last one was the line angle structure. And then lastly, we have D, which is really just a hexagon. Once you know it's a hexagon, you can probably tell that it has 6 corners or 6 carbons, and so this is cyclohexane,